Adventures with Arrows, an introduction to vectors. Vectors are mathematical objects that are fundamental in understanding various physical phenomena. They are not just abstract concepts but have real-world applications that make them incredibly useful. They have both magnitude and direction. Think of an arrow. The arrow is a perfect representation of a vector because it visually shows both how much of something there is and in which direction it is going. The length of the arrow represents magnitude. This magnitude can be anything measurable, like speed, force, or even distance. The longer the arrow, the greater the magnitude. The direction the arrow points is its direction. That's a vector. This direction is crucial because it tells us where the force or movement is headed. Vectors help us understand movement and forces. For instance, when you push an object, the force you apply can be represented as a vector. This helps in calculating the resultant movement. Imagine a boat on a river. The boat's movement can be broken down into vectors. The boat's motor propels it forward. This forward movement is one vector. The river current pushes it sideways. This sideways push is another vector. We can use vectors to represent these forces. By combining these vectors, we can predict the boat's actual path. Vectors are useful in many fields. Engineers use them to design structures and machines, ensuring they can withstand various forces. They are essential in physics, engineering, and computer graphics. Physicists use vectors to describe forces and motion, while computer graphics designers use them to create realistic animations and simulations. Understanding vectors opens a door to exciting mathematical adventures. Whether you're solving complex problems or creating stunning visual effects, vectors are a powerful tool that can help you achieve your goals. Unmasking the vector, understanding magnitude and direction. A vector's magnitude is its size. It tells us how much. In our boat example, the motor's magnitude is its speed. A stronger motor means a larger magnitude. Direction tells us which way. For the boat, the motor's direction might be straight ahead. The current's direction could be sideways. We can represent vectors graphically. We use arrows. The arrow's length represents magnitude. The arrowhead indicates direction. Understanding magnitude and direction is key. It allows us to unlock the secrets of vectors. Vector addition, joining forces and finding the resultant. We can add vectors to determine a single effective force that represents the combination of multiple forces acting together. This is crucial in physics and engineering. Imagine two people pushing a car. One person pushes from the front, while the other pushes from the side. Each person applies a different amount of force, and the directions of these forces are different too. One pushes forward with 5 units of force, exerting a strong push directly towards the intended direction of movement. This forward force is crucial for moving the car ahead. The other pushes sideways with 3 units of force, adding a perpendicular component to the overall force. This sideways force affects the car's trajectory, making it move in a different direction than if it were pushed straight. What is the total force? How do we determine the car's actual movement direction and speed? This is where vector addition comes into play. We can use vector addition to find out. By combining these forces, we can calculate a single resultant vector that accurately represents the net effect of both forces. We draw the vectors as arrows. Each arrow represents a force in both magnitude and direction. The length of the arrow corresponds to the force's strength, and the direction of the arrow shows the force's direction. We place the tail of the second vector at the head of the first. This method, known as the tail-to-head method, helps us visually combine the vectors to find the resultant. The resultant vector starts at the first vector's tail. This point marks the beginning of the combined forces effect. It ends at the second vector's head. This endpoint shows where the combined force leads, indicating the final direction and magnitude of the total force. The resultant vector represents the combined force. This single arrow gives us a clear understanding of the net effect of both forces acting together. Its magnitude and direction tell us the net effect of both people pushing. By understanding this resultant vector, we can predict the car's movement accurately, ensuring effective application of forces in real-world scenarios. Vector subtraction, determining the difference between vectors. In this chapter, we will explore the concept of vector subtraction, which is a fundamental operation in vector mathematics. Understanding how to determine the difference between vectors is crucial in various fields such as physics, engineering, and computer graphics. Vector subtraction is similar to addition. However, instead of simply adding the magnitudes and directions of the vectors, we need to consider the opposite direction of the vector being subtracted. This is because subtraction in vector terms means adding a vector that has been reversed in direction. But now, we reverse the direction of the second vector. Imagine our boat again. If the boat is moving in one direction and the current is moving in another, we need to account for the current's influence by reversing its vector. This helps us understand the true effect of the current on the boat's movement. We have the boat's velocity vector. This vector represents the speed and direction at which the boat is moving through the water. It's important to visualize this vector as it helps in understanding the overall motion of the boat. We also have the river current's velocity vector. This vector shows the speed and direction of the water current. The current can either aid the boat's movement or hinder it, depending on its direction relative to the boat. We want to find the boat's velocity relative to the water. This means we need to determine how fast and in what direction the boat is actually moving when we take the current into account. This is where vector subtraction comes into play. We subtract the current's velocity vector from the boat's velocity vector. By doing this, we are effectively removing the influence of the current from the boat's movement, giving us a clearer picture of the boat's true velocity. We reverse the current's vector direction. This step is crucial because it transforms the subtraction problem into an addition problem, making it easier to solve. By reversing the current's vector, we are essentially adding a negative vector to the boat's velocity vector. Then we add the vectors as usual. This means we combine the magnitudes and directions of the boat's velocity vector and the reversed current's vector. The result of this addition gives us the boat's velocity relative to the water. The resultant vector represents the boat's velocity relative to the water. This vector shows us the true speed and direction of the boat, taking into account the influence of the current. This tells us how fast the boat is moving through the water considering the current. Understanding vector subtraction and the resultant vector is essential for accurately determining the movement of objects in various scenarios, from boats in water to airplanes in the sky. Section 5. Scaling vectors, the power of multiplication. We can multiply a vector by a scalar. A scalar is just a number. Multiplying a vector by a scalar changes the vector's magnitude. It doesn't change its direction. Imagine our boat again. If we double the motor's power, we double the boat's velocity vector magnitude. The direction stays the same. Scaling vectors is useful in many situations. For example, it helps us calculate forces, velocities, and displacements under different conditions. Section 6. Vectors in action. Real-world applications. Vectors are everywhere in the real world. In physics, we use vectors to describe motion, forces, and fields. Engineers use vectors to design bridges, buildings, and airplanes. In computer graphics, vectors create realistic images and animations. Game developers use vectors to simulate movement in physics. Understanding vectors helps us understand the world around us. They are powerful tools for solving problems and making new discoveries. Section 7. Mastering vector calculations. Tips and tricks for success. Mastering vector calculations requires practice. Here are some tips. Draw diagrams. Visualizing vectors makes calculations easier. Break vectors into components. This simplifies complex problems. Remember the rules of vector addition, subtraction, and scalar multiplication. Practice, practice, practice. The more you practice, the easier it becomes. Don't be afraid to make mistakes. Mistakes are part of the learning process. With dedication and effort, you can master vector calculations. Section 8. A universe of vectors exploring advanced concepts. Vectors are a vast and fascinating subject. There are many advanced concepts beyond the basics. Dot product. This operation finds the angle between two vectors. Cross product. This operation finds a vector perpendicular to two given vectors. Vector spaces. These abstract spaces generalize the concept of vectors. Exploring these advanced concepts will deepen your understanding of vectors and their applications. Section 9. Conclusion. Embracing the power of vectors. Vectors are powerful mathematical tools. They help us understand the world around us. From the motion of planets to the design of smartphones, vectors are everywhere. By mastering the basic principles of vectors, we unlock a world of possibilities. We can solve complex problems, make new discoveries, and create innovative technologies. So embrace the power of vectors, explore their secrets, let them guide you on a journey of mathematical discovery. The universe awaits.